Okay, so let's do an example with more than one body. We've mostly been doing one body problems. Let's do an example with more than one body. Let's say that we've got two people who are on an icy surface. So this is our icy surface, and we've got two people. Let's say it's a small purple person and a slightly larger green person, and they're on an icy surface. And let's say that you are on the land and you're trying to help them. Whoops, I didn't mean to make the land higher than the ice. So let's say that you're on the land, and this is you, and you are trying to save them. They're on a frictionless surface, icy surface, we'll call it frictionless. And let's say in order to save them, you're going to throw them a rope. And so we'll have a rope. I don't know what color to make the rope. Let's make the rope purple. No, we already have a purple person. Let's go ahead and make the rope gray in this case. So we're going to throw them a rope so that they can attach themselves with the rope and then attach themselves to you with the rope, and you can pull on the rope to get them off the ice. Okay, so let's say that the purple person has a mass of 40 kilograms. We'll call that M1 equals 40 kilograms. The green person has a mass of 60 kilograms. And let's say that you pull with a force of 200 newtons. So you're exerting a force of 200 newtons on the end of that rope. And let's just make it all horizontal so we don't have to worry about two directions for now. And ask two questions. One is, what is the tension in the rope, in the rope at all places? And what is the acceleration of the purple and the green person? So there are actually four questions here, right? What's the tension in the rope here? What's the tension in the rope here? And what's the acceleration of that person? What's the acceleration of that person? So we're looking for four things. Okay. So how do we do this problem? Well, we're going to use the so first of all, we draw a diagram, which is done. That's step number one, right? Then step number two is to draw your free body diagrams, right? And free body diagrams, here we've got well, you can say we've got two masses or three masses, but the only two masses that are moving here are M1 and M2. You're sitting still, so you could draw a free body diagram of you, the person on the land, if you like. But I'm just going to draw a free body diagram of M1. Well, maybe I'll draw free body diagrams of all of them, M2 and you. We can draw free body diagrams of all of them. Okay, free body diagrams is drawing a diagram of each of these separate from the other. So I need to give myself a little bit more space. Let's go ahead and just do M1 to begin with. So what are the forces on M1? How do we know what, so step two, drawing a free body diagram of each mass. We're just going to start with the first mass. How do we know what forces could be on them? Well, there are only a certain number of forces. We've already determined that the only possible forces that can be on somebody is a normal force, a gravitational force, a frictional force, a tension, some kind of external push or pull that you haven't yet determined is one of the other forces that we've mentioned here, and a spring force. So we simply ask about the first force. Is the person touching a surface? In this case, the answer is yes, so there's a normal force. Normal force points away from the surface that you're touching, so it's Fn up. Is the person being affected by gravitational force? And in this case, yes, the person is being pulled down by the gravitational force of the planet. That's F sub g. And that's their weight, right? The gravitational force is, by definition, the gravitational force of the Earth on the person is its weight. Is there a frictional force? No, there's no frictional force on this person because we said they're on a frictionless surface. Is there a tension? Is there a rope attached to the person? Yes, there's a rope attached to the person, and the rope is pulling the person to the right. So we can call that Ft1. That's the tension on person 1. Is there some external push or pull on the person? There's nothing else touching the person, so there is no push or pull other than the ones that we've already mentioned because there's nothing else touching the person. I guess I should have asked before that is there a spring force on the person? In other words, is there a spring attached to the person? The answer is no. So the free body diagram of M1 is as shown. Now we can draw a free body diagram of M2. Is there a normal force? Yes, there's a normal force. Oh, I should have put a subscript on the person N1 because they're different normal forces. There's a normal force on person N2. The gravitational forces are different, so I should have put the subscript Fg1 and Fg2. Right? The gravitational force is the weight. It's defined as weight. We showed that in a different lecture. Is there a tension? There are two ropes attached to M2. There's a rope going to the right. We can call that FT2. Whoops, FT2. And there's a rope going to the left. And we're going to call that FT1. Now, why did I call that FT1? The rope going to the left on M2. It's because it's the same rope as attached to M1. And the same rope has the same tension throughout. That's property of tension. The tension is the same throughout the rope. So if our single rope is attached between M1 and M2, then the tension is the same everywhere along that rope. The tension in F2, even if it's the same rope, the tension in F2 is different than the tension in F1 because the rope is attached to the mass M2, and the mass M2 exerts a force on the rope at that point, so it can change what the tension is. Okay, then we can go ahead and if we wanted, we could draw the forces on you, because I said it's you on the shore, and on you, there's the normal force on you, there's your weight or your gravitational force on you, there's a frictional force on you. There has to be a frictional force, otherwise you couldn't be pulling on this rope. So there's a frictional force on you, FF, which is keeping you from pulling yourself towards those people. If you were pulling on, think about it, if you were pulling on the rope and there was no frictional force on you, yes, you could pull on the rope, but you would be moving towards the people and the people would be moving towards you, right? Okay. And then the rope is attached to you, so the free body diagram of you has FT2 going in that direction. So that's a free body diagram of you. In order to answer the question in A and B, we don't need anything from the free body diagram of you, but that's a perfectly valid thing to do, draw that free body diagram. And that's step 2, drawing free body diagrams of everything. Step 3 is choosing directions. So now we're going to do step 3, and we're going to choose our positive directions. I'm going to choose red for step 3. Actually, let's do step 3. We're going to choose our positive directions, and by convention, generally you're going to find that mathematically the easiest thing to do is to choose your plus x direction to be the direction of acceleration of the mass. So we can choose, actually I've got to be careful here. We will see in the future that you don't have to choose the same direction for each of the bodies, even in the same problem, as long as you're consistent. What I mean by that is if M1 is accelerating to the right, you hope it's going to be accelerating to the right, then I'm going to choose that as my plus x direction. Then my plus y direction can be either up or down, doesn't matter, I'm going to choose up. And then for M2, I'm going to choose a different axis system. Actually, I'm going to choose the same axis system, but I'm going to choose the plus x direction to be the direction of acceleration of M2. So if M2 was for some reason accelerating in a different direction, I might choose a different axis. So choosing the directions plus x and plus y, and same thing for you're not accelerating anywhere, and you're not going to matter, but so I'm just going to go ahead and draw plus x to the right and plus y up. Okay, so choosing your directions, that's step 3. Step 4 is simply identifying, and this is for the sake of you and the work you do later and me when I'm grading you, is to identify that we are going to use F net equals MA. So it's writing that down before you write down any numbers and breaking it into components. F net X equals MA sub X and F net Y equals MA sub Y. That's step 4, identifying the relationships you're going to use to solve this problem. And if we need kinematics later on, we can add kinematics later on, but when we're solving a Newton's second law problem, it's F net equals MA. Step 5 is to identify the left-hand side of Newton's second law, the net force from the free body diagram. So step 5, I'm going to, from now on, I'm just going to, let's just forget the free body diagram of U. M1 and M2 are the only ones that are moving here. They're the only ones we care about for part A and part B. And I need to therefore write Newton's second law for M1 and Newton's second law for M2 separately, right? They're two separate bodies. We have to, there's two separate bodies. F net equals ma. F net equals ma is about the force on a certain mass, right? So we can talk about F net equals ma on M1 or F net equals ma on M2. You don't talk about it really. Generally, we don't talk about it on a system of masses. We talk about it on a single mass. So this is for a single mass. Okay, so we want to apply that to M1 or M2. So step 5 is to identify the left-hand side. F net x, let's say for M1. F net x in step 5, F net x. Look at the free body diagram, right? We're going up here, we're looking at the free body diagram, and we're saying what forces have an x component. In this case, it's just Ft1. So for M1, it's plus Ft1. Ft1 is pointing in the plus x direction, so it's plus Ft1. Are any of the other forces in the plus x direction? The answer is no. Let me shrink this down a little bit. Are any forces in the plus x direction? The answer is no. So it's Ft1 equals M1a. Do we know? Well, let me write M1 a sub x, where M1 is 40 kilograms and a sub x is what we're looking for, right? The acceleration of body 1. Okay. For and then that's the x direction. Whoops, that's the x direction for M1 in the x direction. In the y direction for M1, we look at our free body diagram in the y direction. In the plus y direction, we've got plus Fn1. Again, looking at the screen and looking at the M1 circled in yellow, and looking in the y direction, you've got Fn1 pointing upwards, so in the plus y direction, so that's plus Fn1 minus Fg1, right? So Fg1 points in the minus y direction, so I put a minus Fg1. So the plus and minus sign indicate direction, the F's indicate magnitudes, and that's all the forces in the y direction, and that equals M1 a sub y. Where again, M1 is 40 kilograms, but a sub y is equal to what? A sub y is equal to 0 because we chose plus x direction to be the direction of acceleration. So in the y direction, there is no acceleration. That's the benefit of choosing the plus x direction to be the direction of acceleration. So that's for M1, and then we're going to do the same thing for M2. Let's do the one for M2 a little bit quicker. For M2, in the x direction, you've got Ft2 to the right, Ft2 to the plus x direction, and Ft1 to the minus x direction. So look, I'm going to go ahead and circle it in a different highlighter color. Circle it in blue. So we're looking at that one now. In the x direction, I've got, need to give myself some space here. In the x direction, I've got plus Ft2 minus Ft1. Ft2 is in the plus x direction, Ft1 is in the minus x direction, and so that equals M2 a sub x, where M2 is, so this is identifying the right hand side. Oh, actually, I messed up. Didn't really mess up. I was just doing step 5 and 6 together, right? Step 5 is to identify the force from the free body diagram. Step 6 is to identify the masses and accelerations. Okay, so step 6, identifying M2 was 60 kilograms. M2 was 60 kilograms, and recognizing that a sub x is the same as for M1, so it's the same a sub x. Because they're attached together, because they're going to move together. It's got the same a sub x. So we've got this equation, we've got this equation, we've got this equation, and then in the y direction for M2, we've got Fn2 up and Fg2 down equals M2 a sub y, where a sub y equals 0. So we've got these 4 equations. We can then now go ahead and plug in and solve for the unknowns. Okay, so I'm going to take these 4 equations, these F net equals ma applied to the two masses M1 and M2, and solve for what we want to know. So let's start with the first one. With the first one, the first equation, ft1 is an unknown and a is an unknown, m is known. So there's two unknowns. The second equation, this actually just tells us fn1 equals fg1 because a is 0. So that's what you get from that. And that doesn't tell us anything that we've asked for. So great, that's what that tells us. It doesn't tell us anything that we've asked for. Same thing with this fourth equation. It tells us that fn2 equals fg2. It just says that the normal force is equal to the weight. Now keep in mind, this is not always true. It is only true for a body which is sitting on a surface and there are no other forces on it, and it's not accelerating upwards or downwards. So this is a special case, but in this case it says that the normal forces are just equal to the weights. So only the first and the third equation are going to be useful because the first and the third equation have the things that we want to know, right? We want to solve for the acceleration, ft1 and ft2. The acceleration, ft1 and ft2. So we've got those unknowns. We've got two equations and three unknowns. Right? So now we're counting equations on unknowns. We've got two equations, the two equations with the three unknowns, right? ft1, ft2, and a. So there must be some more information, and the more information that we left out is the fact that I'm pulling with a 200 Newton force. The fact that I'm exerting a 200 Newton force on the rope attached to M2 tells us what? Because the force, the tension has to be the same throughout the rope, that's a property of ropes and tensions, then it tells us that Ft2 is equal to 200 newtons. That's basically a given, is given, okay? Ft2, the tension in rope 2 is 200 newtons. Because I'm pulling on it with a force of 200 newtons, that means it must be under a tension of 200 newtons. So, that being said, now we've got two equations and two unknowns. If we add that information, we've got two equations and two unknowns. So let me rewrite my equations. So, now we're solving, right? This is step 7. Two equations and two unknowns. I'm just going to go ahead and rewrite them. Ft1 equals m1a. I'm going to drop the sub x because we don't. The acceleration is in the x direction, and we've got ft2 minus ft1 equals m2a. We know that ft2 is 200 newtons, and we know m1 and m2. So we can go ahead and solve these two equations together in order to find A and ft1 in terms of everything else. So I went ahead and solved those together. You do the algebra, check the algebra. I simply did a substitution of ft1 equals m1a into there. And so I did a substitution and solved for A, and then plugged in the known values to get A is plus 2 meters per second squared. And then I can go ahead and take that acceleration and plug it back in to find ft1. So therefore ft1, which equals m1a, is 40 kilograms times 2 meters per second squared, which is 80 newtons. So ft1 is 80 newtons. ft1 is 80 newtons, ft2 is 200 newtons. Acceleration of both bodies is 2 meters per second squared. Done. So I just wrote out the answers there for you.